I thought the best thing to do is we should do now, but maybe we should do one together, and then I will put up a different one, and you guys can try the second one a little more on your own. Okay? Sound good? All right, so I decided to use methylamine. Methylamine is a weak base, and it gives you the formula. You are never expected to memorize the name of any formula, and you are not expected to know that methylamine is a base. You don't need to know that. They'll tell you that. So methylamine is a base. So the first is write the reaction between methylamine and water. So let's see if we can, I'll start you guys off. Let's see if you guys can write down the products on your own. So if methylamine is the base, that means water is the acid. What does the acid want to do? It wants to donate a proton. So think about, if this methylamine gains a proton, think about what its new formula and charge would be. And if this thing loses a proton, think about what H2O's new formula and charge would be. Remember, guys, a proton is basically just H plus. It's an H plus that moves. Right? So take like a minute. See if you can figure out. That's one thing. Yeah, that's right. That's one of them. Yep. So that's this when it lost the proton. So that how would that change that? So just as a heads up, let's take any points. They wouldn't take points off for it because they wouldn't inspection, but that just as a heads up, that's what we got. Right, so when I'm done, remind me and I'll show you what methylamine looks like, and then you can kind of see why it would go there, that's all. So you guys had it right. So methylamine becomes I don't even know what it's called, the methylamine ion, I guess. I'm not sure. But instead of NH2, it's now NH3, and if it gained a proton, if it was neutral before, now it's positive, and when water loses a proton, it becomes OH minus. By the way, because we're producing hydroxides, this solution at the end will be acidic or basic. It's going to be basic because we're going to end up with more hydroxides than hydrogens. Right. So the next question is, determine the pH of a 0.25 molar solution of methylamine. Now, and they gave us this thing called Kb. Now, you guys weren't here yesterday. K is the equilibrium constant. Kb just means it's the constant when it's a base. Ka is if it's a acid. The setup is the same. Now, let's think real quick. If I want to find out pH, I would need to find out either the concentration of H plus or the pOH. Well, guys, look real quick. Based on this problem, are we making something acidic or something basic? So is it easier to go the top route or the bottom route? Because we're already making OH, so we want to go this way. So if I want to find out the pOH, I need to find out the concentration of hydroxide. And guess what? We have something to work with. So now we can link this to that. Well, it's an equilibrium. So K is always products over reactants. And one of our reactants, if it's H2O, is a liquid. Does it apply? No. Here's the other thing. I'm going to get rid of this real quick. This is on your equation sheet. The basic formula for an acid is Ka equals H plus A minus over HA. Let me see if they give you the base one. They do. Even better. Same thing is true for a base. So for Kb, the basic formula is OH minus, all right, times B plus over B. Is that how they write it? No, they write HB on here. Well, of these two, which one should we use? Left or right? Because we don't have Ka, we have Kb, and we're not making hydrogens, we're making hydroxide, so I'm gonna throw this one out. Well, Kb is 4.4 times 10 to the negative fourth of the hydroxide, the conjugate acid, or the base. Which value do we also know? What does the 0.25 represent? It's just the base. So this bottom thing is 0.25. And when we wrote out our equation, this is always true, for every one methylamine, it makes equal amounts hydroxide and conjugate acid. So if these are both the same and we don't know them, we can give them both what algebraic letter? X, and two x's multiplied together becomes x squared. So we can solve for x squared by multiplying. If you multiply, you get 1.1 times 10 to the negative fourth equals x squared. And then we just have to take the square root, and the square root is a number, because that's how math works. If you didn't know, I know, guys, I'm pretty intelligent. 0.0105. Now, is that our answer? What did we actually find now? Like, what does that represent? We've done a lot of math, but let's make sure we know what we're doing besides just plugging in numbers and just praying. Yeah, but what else is it, by the way, besides OH minus? Technically, it's also what, Mia? Yeah, it's both OH minus and HB plus, but we don't care about HB plus. So if I have this, which is OH minus, I can now find the POH, because I can just take I don't know why I did that, that's weird. So if I take the negative log of this thing, the negative log of 0.0105 is going to be 1.98. That's not the answer though, because that's POH. To find pH, 14 minus 1.98, 12.02. Wow. It's a big question. Wait till we get to salts with this, then the math gets wild. No, it's okay. I know you two guys were here yesterday. I know it still could totally be a complete foreign language at this point. I know you two guys totally missed yesterday. I'm not asking you to be experts or anything like that. I'm not even asking you to have full comprehension. I'm not even remotely talking about that. Is there anything that totally made absolutely zero sense and you'd like to just hear it or see it again? It's okay from anybody, including you. But we can't answer you because you're not there. Fooled you.
I mean, I got it, but I just want to make sure, like, the two equations for, like, Kb and Ka, it's like, the bottom is the total amount, right, and then it's one of the reactants, and then one of the others?
So, no matter what, let me get rid of here real quick. So your basic formula for an acid, forget about H2O, because the water is irrelevant. Like, it's there, but water doesn't do anything for this stuff. And then for a base, you almost kind of have to draw the water. It doesn't make sense without it here. Again, it's not relevant to the problem. We would get this. Because it's a liquid, it doesn't apply to equilibrium. So no matter what, your products is always either H plus or OH minus and the conjugate. So if it's an acid, it's H plus and the conjugate base. If you're a base, it's the conjugate acid and OH minus. Because there's only ever two products, you always get at the top H plus and A minus, or BH plus and OH minus. They're always the products of your reaction. And then your denominator, your reactant, is the initial acid or the initial base. So this is just gonna be HA, and this is gonna be B. This is always true. There are no exceptions to this rule. Strong acids are in equilibrium, so they don't do this at all, right? We don't do an ice chart for a strong acid, because if we know the concentration, if this is a strong acid, if this is 1 molar, this also has to be exactly, because it fully breaks apart and dissociates. So it's not equilibrium, so we don't do this for strong acids or strong bases. But for a weak acid and weak base, this is the setup every time. And that's cool. I forgot that they gave you both of them, which is just nice, because acids are easy, bases are a little weirder to remember. The other thing that everybody always forgets, and you guys are awesome at this, these two values are always the, so if they gave you A minus's concentration, that's the same thing as H plus, and I have seen over the years where that's the starting key, and kids have no idea what to do. Because they'll have like this and this, and it'll say find Ka, or I'll give you Ka and this, and it's like, or I'll just give you this and start with find the pH. And so remember, these two values are always gonna be the same, okay? Should we try another one? All right. Let's look at this. Ka chart, weak acid. There's a better list. Oh, here we go. Let's pick an acid. I don't know. Oh, you guys can't see them. Here's a whole list of them.
Uric.
Should we do uric acid? All right, uric acid. All right. Wow, that's a pretty crazy looking formula. All right, so let's take uric acid. So we have a sample of uric acid. This is the Ka value right here. By the way, for my friends that were here yesterday, what do you think this represents? How do we take a number that's got an exponent and turn it into a non-exponent number? We take the negative log, and in chemistry, if you take the negative log, we put what letter in front of something? Lowercase. How do you find if you take the concentration of H plus, you take the negative log, it's called the pH. So if this is the Ka, this is called the pKa.
Oh, dude, that was in the video.
Yeah.
I know. I know, it's okay. That's why I did it. It's cool. Thanks. All right.
Okay.
Look at this great ad. You could look younger. Apparently you could just wear this. This seems like a very stupid outfit to wear in the woods. Get bit everywhere. And sunburn everywhere. That's very dumb. I don't know what this is about. I loved the sun. I don't like the sun anymore. We took an iron to the face and got rid of my wrinkles. I'm not really sure. I love all these weird things that show up. All right, anyway, so we have uric acid. That's the Ka value. So here's my question for you guys. All right, I have a sample of uric acid. Turns out my sample, the pH, okay, is 5.2. So here is what I want you guys to find out. Can you tell me what was the concentration of the initial uric acid? So I'm telling you the pH of a sample of uric acid is 5.2. Based on the fact that you know its Ka value, and you know how uric acid will dissociate into water, right? Can you work and find out what is the concentration of the initial uric acid? That is what I am getting as the answer. You got it. There you go. Can't use this. We have to get it out of here. What's that? 10, no, that's so to get out it's 10 to the negative, so you 10 to the negative 5. Yeah, pretty good. Whatever that is on top, and then when you find is that this, or is it both? So whatever number you get from the math, what we have to do is memorize your multiply them together. You got it. We still have 17 minutes left. We got 28 is out of here, so we're adding the time to that. You got it? Val, you got it?
Yes.
This is up top, square root of X is at the bottom. Yeah. H plus. This is the goal.
Oh, wait, but then, okay, I was thinking this, but then I was thinking like, I was thinking the same,
They are.
and then you know that,
So
oh, and then square, oh, okay. Okay. I was going around that, but like, thinking like, oh, it's this lady who does like senior photos, but she has like a web team. And my friend told me to apply to it, so I did.
very very cool to look at the woods. They're all like coming down and they're
Oh, yeah.
yeah.
Maybe that's what they were doing. I meant to put that.
All right. To the bottom, so this is the square. This is just x. So this part will be squared. And then what would you do with these two things? They can just create pencils. So we use this square divided by that.
You were yes. You only have one.
I was listening to a song, though. I was listening to dreams. I was singing a song, I was screaming it. Right back there at the same time.
Yeah, that's what you thought, and only me.
All right, so we were trying to find out the concentration of our acid initially, which in this case is HA. We knew Ka. What's the value of Ka? I got rid of it.
1.3 times 10 to the -4.
You got it. Now, this is our goal. We did not know H plus or A minus initially, but we were given the pH. So, pH was 5.2. Well, we can do 10 to the negative 5.2 is going to give me the concentration of H plus. And what else is this the concentration of? A minus. So whatever you get for this, so when you multiply, or when you do this, you end up with, was it 6 something? 6.31 times 10 to the negative fifth? 6. And then because it's both, it's got to be this quantity squared. Mathematically, you can trade the x and this. These can flip-flop, and then when you divide, you got that really, really small concentration. Super small concentration. Guys, this Ka is relatively big. So for a weak acid, it's on the stronger side. So that's why such a small concentration was used, right? That concentration is minute, very, very small.
Yeah.
Good?
Yes.
Okay. At this point, for the rest of the time today, because there's not a ton of time left,